apologies for my pronunciation. Our second speaker is Syed. He's currently a research fellow, a Florence Nightingale Bicentenary Research Fellow in Computational Statistics and Machine Learning at Oxford, at the Department of Statistics. And his research includes contributions in the fields of sampling methods, smart Monte Carlo sampling methods, scalable Bayesian inference, and annealing algorithms, which I believe he's going to talk to us about now.
Thank you for the introduction. Yeah, so today I'm going to be giving you guys a talk about how to do scalable inference using annealing and annealing algorithms. So the fundamental problem that I want to be discussing today is we want to compute an expectation. So suppose I have some complicated probability distribution. Maybe I can evaluate up to a normalizing constant. I have some general function, and I want over some general state space, and I want to be able to compute that number. In practice, one of the most successful techniques that we have is MCMC. So you pick your favorite MCMC algorithm, run it for a very long time, and then you get the output, and you use the fact that it's there's an ergodic theorem, so there's a lot of large numbers, so when you average it all out, you get a number and you're good. That's what the theory tells us, and that's what we tell ourselves. But anyone who's ever implemented an MCMC algorithm knows that it's a bit more complicated than that. In practice, this is what actually happens. Right? You run it, and you can trick yourself into thinking that you've actually converged, when in reality, you're dealing with maybe multimodal systems, and you got trapped in one region of local high probability and completely misregarded another. But the amount of time that it takes to jump from one local region to another high region is particularly large, because in order to do that, you have to travel between a very low probability region. So this problem gets only worse when you're dealing with higher dimensions, constrained state spaces, weird topologies. And the bigger issue, in my opinion, is also the fact that you don't know a priori how bad the problem actually is. So that's kind of the reason why you're running something like this, to actually figure that out. So in the context of, say, Bayesian inference, multimodality comes up all the time, in the sense of a local region of high probability corresponds to a plausible explanation for your observed data for the model that you have. Again, in an ideal world, everything is properly specified, but not everything is always like that. So I want to make an argument that one of the foundational reasons as to why MCMC fails is the fact that it's serial. There's both a hardware and an algorithmic perspective on this. So from a hardware point of view, clock speeds have stagnated over the last decade. Your computer right now isn't that much faster in terms of clock speed as it was a decade ago. The big difference between your laptop now versus your laptop back, again, a decade ago, is the fact that you have way more computers within your laptop. There's a lot more parallel processes, and that's where we want to be able to exploit that fact. MCMC is inherently serial, though, which makes it really hard to capitalize on this modern computational resources that you have. So for example, so in MCMC, by definition, is building a Markov chain, which in order to know where to go next, needs to rely on the information that you have now. So you can't really peek ahead into the future, and you can't pre-plan where you want to be going. So I want to make an argument that we can take advantage of the fact that we have multiple computers and delegate the task of actual exploration towards a reference distribution or reference chain that is just designed to be exploring. And then we use an intermediary, these are other parallel threads to run other Markov chains that are targeting not the target itself, but an interpolating distributions in between. So by building this sequence of potentially more complicated problems, we're effectively delegating the task of exploration to a reference, and we're just letting the target chain be responsible just for accuracy and not have to do both. So that idea that I described to you is called annealing. So annealing is motivated by physics, where the target would be considered the cold distribution, and then the reference would be considered the hot distribution. But I want to abstract that away a little bit. So in our case, pi1 I'm going to denote as the target, pi naught I'm going to denote as the reference, and then pi beta is going to be our interpolating path of distributions. where beta is some continuum. There's a canonical way of doing this, what I call like the linear path, where you're linearly interpolating between the log densities in block space, or geometrically interpolating, but there's many other possible paths to pick, but this is the one you should think in the back of your head. So you can already see, like, so this is the left-hand side is the diagram of like, you see all the distributions simultaneously. So at the top, you have your target, which is your bimodal distribution, and at the bottom, you have your reference, which is like a unimodal one. So you can already see, like, by effectively adding this extra dimension, like, to play around with your beta, you effectively turn your complicated multimodal distribution in whatever space you're in into a unimodal distribution in one dimension higher. So this effectively, like, using this annealing path, you're effectively creating a tunnel connecting the different modes. And if you have figured out a mechanism of actually traversing this path, you have now created a way of actually maybe mixing between the different modes in a reasonable amount of time. Because MCMC generally does work well in unimodal settings, with caveats. So in practice, we don't live in a world of where we can just run continuums. We have to discretize. So what we're going to be doing is we're going to be cross-sectioning this. So like we're going to pick a schedule of betas, which I'm going to call the annealing schedule, which interpolates from beta equals 0 to beta equals capital N, where capital N is the number of interpolating distributions. So again, this is an annealing, but an annealing itself is it's an ingredient. It's not an algorithm itself. It's a platform to build algorithms on top of. There is an entire wide class of algorithms that exploit this annealing idea, a common one being diffusion models recently. But today I want to give a talk about on one that I've worked a lot on called parallel tempering. So parallel tempering is essentially taking our MCMC problem that we had and making it way more complicated. So instead of solving one problem, we're going to solve n of them. But the way we're going to do this is we're going to construct a new Markov chain, not just targeting our state space, but targeting a vector of state spaces, where the nth component is going to be corresponding to the nth annealing distribution. So if I want to recover my expectation that motivated all this, I can just marginalize out and just take the last component. And if I construct it in a way where the station distribution is targeting everything correctly, then I still recover back my expectation. So how do we actually construct this? Well, we're going to do this in a two-step procedure. So every iteration of parallel tempering is going to do the following. We're going to first do a local exploration move. So again, parallel tempering is a meta algorithm, so the input in is an MCMC algorithm, so targeted to your particular problem. And then, so at every component, there's n of them, I'm just showing you two, you're going to apply your local move. And notice the one that's closer to the target gets maybe trapped in like its little mode, and the one that's closer to the reference is able to make a traversal because it's a bit flatter. Well, then up until that point, if I just did the local exploration, nothing special has happened yet. At that point, I've just basically done more computation and haven't really like made an effort to like target the distribution that I want to. So all the magic of parallel tempering happens in this step, the communication step. So with the communication step, what it allows you to do is it allows you to propose a swap between adjacent distributions where you are essentially allowing communication to occur. So you're not always going to accept. You have to do some type of metropolis correction to ensure that the station distribution of the global dynamics are preserved. So if you reject, well, you technically only did a local exploration step and you've lost nothing, other than the fact that you had to propose a swap, which is not that bad. However, if you accept, there is potential magic that can occur. So if you have an acceptance, like the acceptance probability only doesn't really see which mode you're in, it only sees the relative likelihood. So notice how in this case, if the acceptance occurred, even though I started off at the left-hand side towards the target and the beginning, in one iteration I was able to go to the right-hand side. And that wasn't because I was good at exploring during the target, it's because the reference was better at exploring. So this idea, if you like extrapolate this up, instead of just doing a single swap, but you do many of them, then you get a parallel tempering algorithm. So to go back to the motivating example that like showed this alpha. So if you had like your single chain MCMC algorithm, if you run parallel tempering correctly, this is what you can end up getting. So notice how not only do you make the traversal between the different modes, but you do so reliably and often. And this isn't just like a simple toy Gaussian problem. This actually happens pretty reliably in practice as well. So these are 4 different examples of very complicated multimodal problems in various dimensions. And I'm just showing a cross-section with 1 chain on one side and 50 chains on the other. So hopefully at this point, I have like motivated enough that parallel tempering is at least like interesting and worth thinking about. So now I've left a lot of details on the work, so let's like start talking about those. Right, so the first one was like, how do I actually like tune parallel tempering? Parallel tempering is like again, there's a lot of different moving parts, and it turns out it's quite fragile if you kind of mess up any one of them. So in particular, like I showed you how to do a swap, but I have n chains, so how I propose the swaps and the schedule I do the swaps, that matters a lot. So the way that people traditionally did this was called what I'm going to be calling a reversible parallel tempering algorithm. So what you would propose swaps, essentially trying to appease reversibility. So what this would involve you to doing is close your eyes, you pick 2 adjacent distributions at random, then you propose a swap, and then you close your eyes and do the same thing over and over again. And if you look at the trajectories, like you actually end up getting, so if I start off at towards the target at if I'm going towards the target at 1 iteration, because of this reversibility, the next iteration I can also go backwards. And every iteration I can go forward or back, which basically means I'm communicating between the reference and target through a random walk. And anyone who's worked with random walk knows that if I have a random walk with n states, it takes about O(n) squared iterations to make a traversal. So that's bad because if I increase the number of chains, that means the diffusivity that's inherent to a random walk is going to start to kick in, and it's actually going to give you a relatively worse performance. Here, going from the top to bottom, that's a good thing. So when you add 100 chains, you actually get worse performance. So what people thought was endemic to parallel tempering algorithms inherently, which made it really challenging to tune. For example, to work with this inherent diffusivity, you needed to really be carefully choose your annealing schedule. And the state-of-the-art methods before this for reversal PT, where you would reject basically 77% of your swaps, which feels unsatisfying when you want to capitalize on your resources that you have efficiently. How do you actually pick the schedule? Well, this required, because you couldn't take advantage of the stability that comes with having a lot of chains, meant that you had to do stochastic optimization techniques, which were fragile and made your life very hard. How do you pick the number of chains? Well, again, because of this inherent diffusivity that you're trying to tackle, like you had to try to be as small as possible. So picking 10 was not an unreasonable design choice in the beginning, and maybe you're trying to go lower over time. This is the one that I think is a really important problem from a practitioner's perspective, right? So some problems are just hard, whereas some problems I did a bad job implementing. How do I know which regime that I'm in? And so actually getting diagnostics that can actually tell us when the problem is hard or like we need to work a bit harder. So to tackle this, we first need to talk about what does it mean to tune parallel tempering. So tuning parallel tempering requires, I want to again make the argument that it's all about the communication. So I want to maximize how many samples from my reference actually make its way to the target. So if I have like n machines, and each like machine is going through its various swaps, and each has like its particular annealing parameter, after every iteration, essentially you're swapping annealing parameters along the way. So I want to essentially so this random permutation that's occurring over time, like you can use that to actually quantify the communication that's happening between the different chains. So whenever there's information that goes from the reference to the target, so that bold line, I'm going to be calling that a restart. So what I want to do is I want to figure out, my objective function will be to maximize the total amount of restarts that occur, so the percentage of samples in general that make its way across. This also directly correlates with the effective sample size, and we're going to actually put out an archive in the next couple of weeks that formalizes this. So the solution to this turns out to be a 2-line algorithmic change, where instead of proposing swaps, closing your eyes, proposing swaps at random, you first propose an odd swap and then an even swap. then an odd swap, and then an even swap, so doing the deterministic alternation. So odd swaps are going to correspond to swaps between chains n and n plus 1, where n is odd. And the even swaps are going to be swaps between chains n and n plus 1, where n is even. So notice if I do odd, even, so on and so forth, what ends up happening is that if I start off going towards like maybe the target or reference in one direction, the next, because I can't propose the same swap twice, I can't go backwards, at least not in one iteration. So there's an inherent momentum that's being built into the trajectories of parallel tampering when you do this deterministic even odd swap. And what ends up happening is that when you like scale it up, like you completely eliminate the diffusivity. So you go from like actually like getting worse performance by adding too many chains to actually getting more stable, better performance, which basically means, and you can formalize this, like if you can actually quantify what the restart rates look like. So Rn is a rejection rate. So essentially, like you can show that the total restart rate is essentially going to be 1 over 2 plus the sum of the odds ratios of the rejection rate. So if even one of the rejection rates is bad, you're going to get terrible results. But if you crank up the number of annealing distributions to n, and like the annealing schedules to be sufficiently dense, you actually start to stabilize and converge to a constant. So what this means is that, first of all, like with this non-reversible mechanism, you actually get stable performance and you improve and can capitalize on the computational resources that you have, although with marginal gains. You can quantify those marginal gains and the actual efficiency of parallel tampering using this number lambda, which I'm going to call the communication barrier. I'll go into a second what that means. What this also means is that we can actually like take advantage of this robustness that comes from increasing the number of chains. So this stability means that we can use this to our advantage to actually like figure out what the optimal schedule should be. And we can also now use this to scale up to GPUs and actually take advantage of the modern computational resources that we have. So to give you an idea of just like how this differs as you increase the number of chains, so the top is reversible, bottom is non-reversible, it's the only difference. So notice how as you increase the number of chains, the top starts to get worse, whereas it gets a bit better and then worse, whereas the non-reversible just only gets better. But again, with marginal gains. So what is this communication barrier? So all of this boils down to figuring out, again, what is the communication between adjacent distributions corresponds to understanding this rejection rate. So if I view the rejection rate as, you can interpret it as a divergence that essentially quantifies the overlap between different distributions. So when there's a lot of overlap, the rejection is small. When there's very little overlap, the rejection is almost close to 1. It's very closely tied to total variation. So you can talk about the communication barrier. So first, in terms of the local communication barrier, which is essentially quantifying the instantaneous rate of change of your rejection rate. So you can interpret it as a derivative of your rejection. So the little lambda corresponds to how sensitive your annealing distribution is to small perturbation beta. Whereas when you integrate that is how you get this lambda. So essentially, you can interpret this like lambda, this communication barrier, as the cumulative rejection along your path. Moreover, you can actually, like these aren't just esoteric like theoretical quantities, you actually can get them very efficiently from the output of the statistics that you're keeping track of anyway. So if I take the sum of all the rejection rates, again, which I'm keeping track of, that gives me a very good approximation of this lambda. And so now we can, if we pretend that approximately equal to is an inequality, then you can start to like reframe this as a constrained optimization problem where I want to maximize the total number of restarts with the constraint that the sum of the rejection rates equal to lambda. So this gives us that the optimal schedule is essentially trying to integrate this local communication barrier such that it's a constant. So if I can figure out this lambda, then this now becomes a one-dimensional like problem to actually figure out one-dimensional bisection essentially to figure out what this like optimal schedule should be. So this is, for example, an easing model where you have there's a phase transition that occurs where there's like a lot of sensitivity towards this critical threshold. So like the optimal schedule, what it naturally figures out is that you want to be putting more distributions where there's rapid changes occurring. And you want to be spaced out the distributions a bit further where there's a bit more stability. So the algorithm essentially is you run parallel tampering with whatever schedule that you have. You get an approximation of your rejection rate. you can take this cumulative sum of the rejection rates to essentially figure out your integrated communication barrier, do some like monotonic smoothing, spline, and then just do an inverse transform to figure out what the optimal schedule should be. That's one round. You repeat that again now with this new updated schedule, but you run it maybe twice as long, so you get a better refinement of your rejection rate, and then repeat that over and over again. So over like about 10 rounds roughly, like you start to see that your schedule starts to stabilize and figure out where it needs to be. And over time that the average rejection rate starts to like, once this starts to stabilize and the communication barrier starts to also stabilize. So in our JRSSB paper, we benchmarked this against 16 different models ranging from a baby toy easing model to 190,000 dimensional phylogenetic cancer inference data set. So we've tested on a zoo of variety of problems, and in each of these different scenarios, you start to see the average acceptance probability starts to stabilize within like 10 rounds. And then 10 rounds, roughly 10,000 iterations, which it's not uncommon to run an MCMC algorithm for 1 million or millions of iterations, so it's actually very negligible. You can also see what the local communication barrier looks like and for a variety of problems. So like the main interesting thing here is that there isn't a single one schedule that's going to solve every single problem, but the fact that this figures out all the weird complexities that can and do occur, I think is quite interesting. It also is now competitive with the state of the art, with like annealed importance sampling and sequential Monte Carlo samplers when done correctly, and oftentimes, depending on the computational constraints you're working with, can often perform better. This is an example of the log normalized and constant estimator that you also get as a byproduct of this parallel tempering algorithm, compared against annealed importance sampling and sequential Monte Carlo samplers. And you start to see, again, it's quite consistent, and it actually is doing the thing you expect it to do. This is another example of, so this was from an astronomy problem that a collaborator was working on. So in this physics world, like in the astronomy world especially, this algorithm called nested sampling is kind of the state of the art. This pair plot on the left is an example of, let's say, like a lot of big decisions and millions of dollars of funding was like spent based off of this type of plot. When they ran like our parallel tempering algorithm on it, you notice how you discover a lot of different nooks and crannies that you miss with the nested sampling. But when there are cases where it does recover the same thing, because so in general, like it's very rare that when you're dealing with complicated problems where you get unimodal distributions pop up, and especially modern Bayesian inference. And another thing we noticed is that we get about an order magnitude improvement in terms of efficiency even when you are using a reversible parallel tempering with our schedule tuning update, but you get about another order of magnitude improvements from also using this non-reversible mechanism. This is from a 30-dimensional phylogenetic inference problem from a copy number inference problem from a cancer data set. So notice how when you're doing this like posterior predictive, like the non-reversible PT was able to discover that sliver of mode. And so like we also find that it works quite surprisingly very effectively at like non-identifiable problems as well. In practice, we also see an improvement when compared to, like, so the restart rates are the thing that we can analyze, but the thing that you often care about as a practitioner is the effective sample size. And what you find in practice, the effective sample size also improves compared to the state-of-the-art parallel tempering algorithms on the order of 10 to 100x in the applications we tried again. In the last couple of years, it's been very cool to see actually this stuff being utilized at scale through a variety of applications completely independent of our own research. So this has been, for example, in the cancer world, they've used it to model single-cell cancer genomes at the evolutionary level to essentially figure out the evolutionary structure of cancer. In epidemiology, this has now been gaining a lot of popularity. So this has been recently applied to discover genetic variations in malaria. An interesting one that I've been really found like fascinating was in the political science world. They've been using our work to identify gerrymandering in various congressional districts. So this is the last application, then I'll call it. So the biggest application of our work has been with the Event Horizon Telescope. So the Event Horizon Telescope was the collaboration in 2019 that generated the first image of M87, the black hole photo that some of you may have heard of. So in the background before so that original photograph came out before our work, but it did use parallel tempering in the background because it's a highly multimodal and Bayesian inference problem. In 2020, they implemented our work, and they were able to recreate the results of the photograph in about 45 minutes from about 5 days. So about 2% of the computational effort. This was independently verified and benchmarked in Paul Tita's PhD thesis, where he actually went through benchmarked our work against what they were doing in the past. So this is an example of the green is what they were doing in the past. So the left, the y-axis is the log likelihood. So higher is better. So they found that after implementing our work, as well as improving their local exploration kernel from, say, their differential evolutionary sampler to an HMC, they were able to get to the blue up there. Recently, this has now been used to recreate the result of the black hole photo of both M87, as well as generate the first image of Sagittarius A star in 2022 and beginning of this year. And they also have now used our work as an instrumental tool to discover magnetic polarization in both M87 photograph and the Sagittarius A star one. So the Sagittarius A star photograph, the paper came out. This was released 2 weeks ago. So if you guys want to check out, I think CNN had an article on it. So this was just kind of the preliminary of parallel tempering, but in the last couple of years, there's been a lot of work being done, both from my group. In particular, we have had work talking about how to optimize the schedule, the communication, the annealing path, connections to variational inference with a reference. We have now a scalable open source package in Julia. And in the next couple of weeks, you'll be seeing a paper on the theory of the actual connection to mixing times, as well as the unification with AIS and SMC. Thank you.
I'll take 2 questions if there are any. All the way at the back, okay.
Hi, really interesting talk. Does it always work? Are there situations where it would be actually less good to do this than a kind of vanilla MCMC? Sounds a bit like a kind of free lunch. Is there any hidden cost anywhere?
So I would say that there are no scenarios where it's going to do worse, but it also depends on the computational constraints that you have at your disposal. There is a cost that you're paying, right? You are actually taking it. It requires additional parallel resources that you could have been using other places. So there's this work that I'm going to be putting out literally in the coming weeks. But turns out there is this phase transition that does happen where if you don't have a dense enough schedule, so where that lambda number, essentially if you have less than lambda number of annealing distributions, it's actually not worth doing parallel tempering at all because you're going to get effectively terrible results. But there's a critical threshold where when you meet that, so essentially if you want us to compute an a normalizing constant, if you have less than lambda number of annealing distributions, the amount of time they need to run it for to get a stable variance estimator is going to be exponential in lambda. However, as soon as you meet that threshold, then it drops down to a linear runtime. So that's kind of the payoff. If you do not have enough computation, if you do not have enough annealing distributions to be on the scale of your lambda, which is a difficulty of your problem, then you are wasting a computational work. Thank you.
Okay, thank you. So, okay, is it quick?
Thanks a lot. I wonder what is the largest dimensionality of benchmarks you have run? Asking this is, it can be quite harder to construct effective annealing schemes in higher dimensional target distributions.
Okay, can you repeat the question, sorry?
The question is about dimensionality.
Oh, dimensionality.
So what is?
So we've got this to work on the hundreds of thousands of dimensions, but I don't like thinking about dimensionality necessarily as a measure of difficulty, because like that lambda accounts for the dimensionality as well. In general, as you increase the dimensionality of your problem, the lambda will grow above square root d. So I think for example, I can give you a one-dimensional problem where it's going to destroy any MCMC algorithm that you toss at it. I can also give you a very high-dimensional problem where it's going to work very well. So I'm trying to, I guess, reframe the notion of difficulty and efficiency to this lambda itself, which again accounts for the difficulty intrinsically that is measured through the eyes of parallel tempering.
Okay, thank you very much.